Okay, so the problem sets are online. If you, again, let me just quickly show you for the first time how to access them. I'm not going to show you every time, but it's the first time. So just go to the website and go to the today's date. It's hard to organize it, but I don't have time, so you're going to have to search through. Let's see. Yeah. So, yes?
Is there a possibility that we can change the time for
The review?
yeah.
That's much harder. But there are two options, Mondays or Fridays.
Work on both days.
Okay. Yeah. Well, come and talk to me about it later. I'm not sure if there's a solution because it's very hard to schedule for everybody. Okay. Yeah. Come talk to me after the class. We need to finish. So the problem sets are online. If you just click on it, it's just a PDF. Okay. And the problems are from the text, but so you need to definitely solve it. The important things are make sure you show your steps. So it's okay if you make mistakes, but I want to understand how you actually process the problem. Okay? So it's online. They're due on the 28th at the end of the day. So you can hand it in as a paper, email it, whatever, but to the address for the class. Okay. Also, before I go on, I posted a number of links on the website which goes through some of the very basic stuff on orbitals, electrons, atoms, the periodic table. I recommend watching them. They're very short. They're like 5 to 6 minutes, 8 minutes or so, and they are mostly aimed at high school level physics, basic undergraduate physics. So this is mainly a review for you. Okay, so if you're totally lost, start here. That's my recommendation. Okay, so let's get started today. You have to speak up. No, just email it to the address. I forget. Yeah. Yes, yeah. Or you can hand it in by paper to me. Or I guess it's Monday, so just either bring it to my office or drop it with the department. Okay, I'll make sure they know if you're going to drop it off.
So there isn't a box?
I don't know if there is. I haven't taught an undergraduate class. There might be a box. I'll find out. I'll let you know on Thursday. That's a good point. Okay, is that clear with everyone? The problems are fairly straightforward. So follow the text, follow the lectures. Let's do them. If you're stuck, certainly come to the review session and ask, okay? That's what it's for. All right. Oops, I gotta... Okay, so today we are going to learn a new concept called energy bands in semiconductors. This is the first step in understanding currents in solid-state devices. So that's the main goal again. So this is week 2, Tuesday. So again, keep the goal in mind that we are trying to understand here. Remember, we started with basic quantum mechanics last class. Now we're going to apply what we learned in order to understand how electrons behave in atoms and later on in crystals. They're different. Okay? So particularly, remember, in atoms, we know they have very discrete energy levels. And we will learn today that in crystals, you have energy bands, continuous distribution of energy levels, not just a single level. And those things make a very, very big difference to the electronic properties of materials. So we need to really understand this conceptually. Okay, the mathematics is not terribly important. So in particular, how do electrons behave in semiconductors? This entails understanding the energy levels of electrons in crystals, essentially. Okay. So first, we have to start with energy levels in atoms, because we need to understand this quantitatively. Solving Schrodinger's equation for crystals is very difficult. It's almost impossible to do it. So we start with atoms, much simpler systems, and we can actually solve them by hand. Okay, and for the simplest atoms, not for any atom. So the simplest atom, of course, is hydrogen. Remember, hydrogen has 1 proton and 1 neutron, so +1 charge on the nucleus and 1 electron circulating it, right? So in order to understand the energy level of the electron, we need to solve Schrodinger's equation for this system. Okay, so we have a potential, we have a wave function, we solve, okay, like we saw last class. So the Schrodinger equation looks like this. On the left-hand side, remember, it's energy, but this is the time-dependent form of energy, where psi is the wave function which describes the electron in this system. Okay, R and T are the space and time coordinates. R is 3 dimensions, so it's x, y, z, or as we will see, it will be the spherical coordinates. Okay. The right-hand side is the operator which determines the kinetic energy and the potential energy. Okay, so kinetic plus potential is the total energy. Straightforward. Okay. The kinetic energy, of course, is given by 1 over 2m h bar squared times this called del squared, which is, remember, is partial over partial x squared plus, so for reminders, this is nothing but that. Right? And then you have it's an operating term, so it's operating on something, right? In our case, it's operating on the wave function. Okay? Now, we solve this equation, we find solutions to the wave function, and once we know the wave function, we can just do this calculation. Take the wave function, use this operation to operate on the wave function to calculate the allowed energy states. That's what we're trying to do. Okay, so keep that in mind. Again, the math is not so important, but I want you to understand the concept, what we're trying to do here. Okay, so first of all, we have to make to simplify the problems, we have to make some assumptions. The first assumption is, remember, the hydrogen atom is spherical. That's the very basic assumption. We have a proton and a neutron and an electron circulating, almost like a sphere. Okay? It's not necessarily very accurate in the most rigorous sense, but that's an approximation. Okay? What allows you to do is that now we can use spherical coordinates instead of x, y, z. So that simplifies the equations a little bit. Again, it's a mathematical trick, and you don't really need to understand how to do it. I mean, I don't really care if you can do the math or not. I want you to understand what these things mean. Okay? So first of all, of course, the potential is spherically symmetric because you have a proton and then electrostatic field in 3-dimensional space. Okay? And this is something you've learned in your high school physics, right? This is 1 over 4 pi epsilon naught, the Coulomb constant, times q squared is the charge of the proton divided by r. Okay, this is the potential that the electron sees in the presence of the proton. And it's negative because it's an attractive force. It's a stable system. You have a proton and you have an electron. Okay, it's spherically symmetric. The spherical coordinates are these, and we'll come back to these, just so you know. R is the value of the radial location. Okay, that's the point of interest. Its coordinates are r, theta, and phi. Okay, theta is the angle within this plane, and phi is the azimuthal angle, which determines the location of the plane. Okay, you may not be familiar with spherical coordinates, so just keep that picture in mind. We'll come back to that when we solve the problem. Okay, the reason to do this is that we can now separate the function into different variables and solve them separately. Remember, we did this last class. To solve Schrodinger's equation, remember, we separated it into space and time. 2 parts of the function and solve them separately. We're going to do exactly the same thing here, but now we are going to separate them according to the coordinates. Okay? Now the coordinates, of course, as we saw before, were r, theta, and phi. So we have 3 functions now defining the wave function. A function that depends on r, a function that depends on theta, another function that depends on phi. Okay, pretty straightforward. We make the assumption that the 3 coordinates the wave function can be separated into 3 different functions, which depend only on the each individual coordinate. Okay, this is an assumption. It turns out to be the correct assumption at the end of the day. Okay, of course, the reason to do this is that if you go back to the Schrodinger's equation, if you can separate the coordinates, as I just said, then these equations become very straightforward. You don't have cross terms. You only have one variable at a time. Just like we saw last class. And you can solve them by hand. Even you can do that. It's not that difficult. We're not going to go through it. But it's just a simple, ordinary differential equation. Second order differential equation. Okay? It's not very difficult to solve. If you're interested, I can show you some text that it's done. So there are 3 separate equations, right? Remember, they're separate, so you can plug this into Schrodinger's equation and you separate them out, the 3 variables, and you get 3 different equations in r, theta, and phi, and you solve them separately. The equations look different, but they are second order ordinary differential equations. Okay? Now, of course, like we saw in the last class, each of these differential equations allows for discrete energy levels. Okay? Which means that the energy levels are quantized. Okay? Which is exactly the same as what we saw on Thursday. Same situation happens here. Okay? So we have 3 different quantum numbers now, because we have 3 different coordinates. Okay? Now let's look, of course, so far it's abstract. Let's look at one very simple example. Okay? We'll solve for this theta, for phi. Okay? That's the easiest one to solve, so we'll solve first. Okay? And everything else is exactly the same way. The equations are slightly different, but the solution approach is the same way. Okay, so for phi, when you separate out the variables, you get an equation which looks like this. Okay? So that's the del squared, right? That's this part in spherical coordinates is the first term. Okay, for phi. So you have that term plus m squared phi equals 0. Now this is a very simple equation to solve because this is a wave equation, remember? This is what we saw last class as well. It's a sinusoid, right? Sine, cosine. In the more general term, you can write this as an exponential, as shown here. Okay, you see that, right? E raised to ij phi is just cos phi plus j sine phi from your complex analysis. I hope you guys remember this. So you see that it's a solution. Okay. Okay, so there are a couple of unknowns here. First, we see there is a quantum number here, m, which is the same as what we saw on Thursday. And we have an amplitude A, which is also the same as we saw last time. Remember last time we had an A cos m something, kxx. Okay, now how do we find the amplitude? Very straightforward. You do the normalization. Remember, the absolute value squared of the wave function, which is just that, integrated over the whole space must be 1, which means that the particle, in this case the electron, has to be somewhere within that range. Okay, so let's go back to the spherical coordinates for a second. Okay, what it's saying is that the electron has to be somewhere between phi equals 0 and 2 pi, or 360 degrees. Okay, that's common sense. So if you take the absolute value squared of the wave function, which remember represents the probability that the electron is somewhere, integrated over the whole range, that has to be 1, because the electron exists. Okay, that's the normalization approach. Exactly what we did for the particle in a box. If you go back and check, remember that example. Okay, okay, so let's keep going. So to calculate that, we just do this. And remember, the phi goes from 0 to 2 pi, so you can do that integral. It's pretty straightforward, right? Take the compass conjugate, put the negative sign, it goes away. Then you just end up with that. A squared times 2 pi. That should be 1. So you now know what A is. A equals 1 over square root 2 pi. Again, remember, I don't need you to memorize any of this because you can look it up in the text. But I want you to follow the logic on how to proceed. I have to think about solving the problem. That's much more important than actually doing the math. Okay? So, and I know a lot of this I might be going through fast, which is why I'm recording it. So go back and view it again. Think about it. Okay? You have to think it yourself in your head, otherwise you will not get it. Okay. So now we know A. Okay? What else do we need to find? M, the quantum number. Okay? Also, that's fairly straightforward because there is a periodicity involved here. Remember, the phi only goes from 0 to 2 pi. So anything more than 2 pi, it has to be periodic. Right? So phi plus 2 pi should be equal to phi. It's a periodic function. Right? Just from the symmetry, it has to be. Okay? With that assumption in mind, we know that the wave function has to be periodic in 2 pi. Right? You go around once, and you go around again. It's the same. If you come back to the same point, the value of the wave function has to be the same. Right? Cannot change. Okay? So the whole thing has to be periodic in 2 pi, which means that we have to make sure that this m phi is a multiple of 2 pi. It's as simple as that. Multiple of pi, sorry. Right? Okay? If e raised to jm phi is equal to e raised to jm phi plus 2 pi. You see that, right? That's what we're doing. Can you see? Okay. The m phi cancels out. Say. Okay. That's a condition for the quantum number, m. Or in other words, m must be an integer. Pretty simple. Okay. So our first understanding of the quantum number is that it has to be an integer. This quantum number. Remember, there are 3 more. Actually, there are 2 more now. We'll see 1 more later. Okay, is that clear? So m can be -2, -1, 0, 1, 2, whatever. Okay. Remember, each of those values represents a different wave function with a different energy level. Very similar to what we did for the particle in a box. Okay. Okay. So at the end of the day, we can solve the 3 equations and come up with 3 different wave functions which get multiplied together to form the final wave function. So you get something like that. Psi in Lm, r theta phi is Rn, so it has one quantum number there. Theta L, another quantum number there. Phi m, another quantum number there. So 3 quantum numbers. We haven't done these 2, r and theta, but they're done the same way as what we did for phi. Okay? And they have different rules based on how the equations look like. Like I said, the equations are slightly different, so the quantum discretization rules are slightly different as well. And I'm just going to state it here without actually solving them. And the quantum numbers are n, has to be positive integers, 1, 2, 3. Okay? L has to be 0, 1, 2, but it is determined by n. It only goes up to n minus 1. Okay? They are related. Yes?
So can it be less than n minus 1?
Yes.
Is it always n minus 1, or it only goes up that far?
It only goes up to n minus 1. That's exactly right. In m, we saw before that they're integers, but they're restricted by the L. It goes from minus L to plus L. Again, I won't go into the details of why they are related. Okay, that's a bit more complicated, but just take it for now. This arrangement of quantum numbers turns out to be the most important thing I would say, it is the reason that life exists, by the way. Okay? This is the reason how the periodic table is the way it is. Materials are able to form bonds and things like that. Everything has to do with this particular distribution of quantum numbers. And you'll appreciate this as we go along. Okay? Now, there is one additional quantum number which is a bit more abstract, and it's a bit more difficult to explain because it has to deal with relativity and solving quantum mechanics with relativistic effects taken into account. But we'll just state it. There's something called a fourth quantum number called the spin of the electron, which you might have heard of. Okay? It can be spin up or spin down. Only two values. Okay? It can be plus h bar over 2 or minus h bar over 2. It actually represents what's called the angular momentum of the electron. It's a quantum mechanical concept. But in any case, you don't need to really understand those concepts, but be aware of it, because this is important. These four quantum numbers are important in determining how electrons will behave in semiconductors. That's why we need to really understand this. Okay? So again, what we have done so far, remember now the wave function here is determined by three quantum numbers plus the s, which is not obvious here. So we have n, l, m, and s, which determines one wave function. Okay? And it determines one energy level. Keep that in mind. So these four quantum numbers determine the energy of the electron. Okay? As you vary these numbers, you get different energy levels. Okay? So you can have lots of combinations of energy levels. Okay? And that's how different elements are formed, as we will see in a second. So each allowed state of the electron in the hydrogen atom is described with four quantum numbers, n, l, m, and s. N is what's called the principal quantum number. It determines the orbit of the electron. It determines primarily how far is the electron from the nucleus. Okay? It's the most important quantum number. Okay, and we'll see what that means when we look how electrons fill the energy levels in a hydrogen atom. Okay? So let's walk through this to understand, because we'll be looking at more complicated atoms in a few minutes. So we need to really understand how electrons fill the energy levels in hydrogen first. Okay? So look at the columns first. Okay? That's N, that's L, that's M, and that's S. S over H bar, so it's plus minus half. Okay? And then the number of allowed states. We'll come to that in a second. Okay? So far so good. The first electron, which goes to the lowest energy level in hydrogen, which is where we expect the electron to be in the ground state, because the systems always like to be at the lowest energy level, will be where n is 1. That's the lowest number you can go. N cannot be 0. If n is 1, L can only be 0. Right? Remember, L goes from 0 to n minus 1. Okay? Let's write that down so we can compare that. Okay? If n is 1, L can only be 0. Right? Because it only goes to n minus 1, and n minus 1 is 0. And m goes from minus L to plus L. But minus 0 and plus 0 are the same, so this can only be 0. Okay? So I'm going to write the rule here. This goes from 0 to n minus 1. This goes from minus L to L. And this is just half, plus minus. Okay? So the first electron will go in here. Of course, there are two states. If you only have one electron, can go into either of them. Okay? So if we look at the fifth column here, allowed states in a subshell, and we'll see what a subshell is in a minute, are 2. Okay? And allowed states in a complete shell. A shell, of course, like I said before, is for a given value of n. It is the orbit. Okay? How many electrons can sit here when n equals 1? It's 2. Right? You can only have these 2. So So you have 2 electrons here, each having quantum numbers given by that or that. Okay, do you see that? 2 electrons in the lowest energy level of hydrogen. The quantum numbers are this or that. NLMS. Okay, this is the simplest thing. We're going to complicate this more, so I want you to be very clear about this. Okay? Now let's do the next shell. Okay? So, and we'll come back to what a subshell means in a second. But let's do the next shell. Okay? So let's say n is 2. What are the allowed values of L? 0, 0, 1. That's it, right? Can only go to 1, n minus 1. Okay? Allowed values for M. Each of these have different ones, right? So this is just 0. This is what? Okay, is that clear? And each of these can have you see that? Right? So how many are there when n equals 2? How many electrons are there? Yeah, so you have 2 here, 2 here, 2 here, 2 here. So you have 8 electrons. Okay, so the allowed states in the complete shell when n equals 2 is 8. Okay. Now the subshells. The subshell refers to a specific value of L. So you can see for this value of L, you have 2. For this value of L, you have 6. Okay, we'll come back to that so it becomes more clear. Okay, so remember hydrogen has only one atom, one electron. So in the ground state, it will of course be in one of these states. If you look at the wave function, right? It will be either one of these. All these other states are available states. They are what are called excited states. So if the hydrogen gains energy, the electron can go up there. Okay? And then it can relax back to the lower states and release a photon, which is what we talked about last class about the atomic lines. Okay? So the electron goes from one of these states back to here. It loses energy and gives out a photon equal to the energy difference. Okay? Okay, so we can keep going this way. So n equals 3, you get 18, and so on and so forth. So you can see. Okay? Now it turns out this rule of adding the electrons is how different elements are formed. So if you have 2 electrons and 2 protons, can someone tell me what is the next element after hydrogen? It's helium on the periodic table. Right? And the electrons in helium gets added this way. These 2 electrons from helium. Of course, the wave functions are different slightly, quite a bit, because you have 2 protons. So you have to solve the Schrodinger's equation all over again. Remember, you have 2 potentials. Now, your potential function is different. But in any case, these rules are consistent. So we can keep adding the electron to form the different elements in the periodic table. Okay? Which is, oh, before we do that, which is shown next, we need to understand a very, very important principle, referred to as the Pauli's exclusion principle. This essentially states, and you can prove this, but we'll just state it, that no 2 electrons can have the same 4 quantum numbers. Okay? In other words, no 2 electrons can occupy the same energy level. Remember, each of these quantum numbers represent an energy level. Okay? Pauli's exclusion principle states that only 1 electron can have one set of 4 quantum numbers. each electron has to have a unique set. Okay? So, for instance, in helium, you cannot have two electrons with these set of quantum numbers. One has to be this, and the other has to be that. Okay? And with these rules, we can build the entire periodic table by filling the electrons. And it explains the whole, most of chemistry, pretty much. Very simple principles of filling these quantum numbers. Okay? We won't emphasize that because we're not a quantum. It's not a quantum mechanics class, but we need to understand some of the basic stuff to understand silicon, for instance, a gallium arsenide, which is what we really want to do. Okay? There is a naming convention which we should be aware of, which is related to what I drew here. Keep this in mind. For N is the principal quantum number 1, 2, 3, and so on. It's just the number that someone uses for naming. Okay? For L, there is a convention for naming is based on some letters. So when L equals 0, it is referred to as S. It's called an S subshell or an S orbital. Okay? 1 is P, 2 is D, 3 is F, 4 is G. We won't really worry too much about very large orbitals because those are mostly transition metals and so on, not very important for us for now. Okay? We'll be dealing with just S and P because that's what silicon has. Okay? So the electron state, instead of writing all the quantum numbers out, can now be written in a smaller form as follows. The last electron can be something like 3p6. But 3 is the principal quantum number, which means n equals 3. P means L equals 1. And 6 means there are 6 electrons in this 3p subshell. Okay, it's just the naming convention. Now, in this convention, the electronic configuration of silicon, whose atomic number is 14, there are 14 electrons, can be written as 1s2, which is the innermost 2 electrons, n equals 1, s is L equals 0, okay? Then 2s2, so 1s2 is just these two, right? When n equals 1, there are only 2 allowed states, so they're filled 1s2, okay? 2s2 are these two, okay? 2s2, the 2 states. 2p6, 6 states. Okay? And so on and so forth. Then 3s2, then 3p2. So the last shell of silicon has 4 electrons. Okay? 2 in the 3s state, 2 in the 3p state. And that turns out to be quite important, as you will see in a few minutes. Okay? Another way to write the same thing is as follows: as neon, which is inert atom, which is all this. Neon in the same configuration is that. Okay, 10 electrons. So this part of it can be written as just neon plus this part, which is the unfilled shell. Just a different naming convention. Again, you don't need to memorize any of this. You can look it up, but I want you to understand where the naming convention comes from. Okay? Remember, these are completely filled shells. Okay? So let's look at this first. Let me drive home that point. If you look at n equals 1, there are 2 allowed states. And if you have 2 electrons, they will occupy those states. They're filled. There are no more states available for n equals 2. Okay? Sorry, n equals 1. Now, if n equals 2, you have 8 allowed states. So if you have 8 more electrons, they will occupy those 8 states. And there are no more allowed states. Okay? Neon has 10 electrons. So it will occupy the first 2 and the last 8. The next 8, I mean. And all the shells are occupied. There are no free states. There are no free orbitals. Okay, that's why it's an inert atom. It doesn't like to exchange electrons. It's in a very stable configuration. All the available shells are occupied. Okay. Okay, this will become clearer as we go on, hopefully. Okay, so this is basically looking at all the elements in the periodic table. I know you can't see it, so I can zoom in. I can emphasize a few things, but hydrogen is very obvious, 1 electron, so it will be at the 1s state. Okay. Helium has 2 electrons, so it will be in the 1s state as well, because there are two allowed energy levels there. Lithium is the next one. You have basically 1s plus 2s1. Okay, 1s2, 2s1, and so on and so forth. So beryllium has 1s2, 2s2. Boron has 1s2, 2s2, 2p1. Boron is important because it's a dopant for silicon. We'll come back to that. So you see boron has an extra electron here, right? 2p1, 1 electron, which it can donate to silicon lattice, which can be used for conduction. So it's a donor impurity in silicon. Okay? And there's carbon, shown here, nitrogen, oxygen, iron, and you see here the neon is completely full. So it doesn't have any electrons that it can take or give. It's an inert atom. Doesn't really react. Okay? Another important impurity for so silicon is here, as we saw before. Is 3s2, 3p2. Okay, that's silicon, just as we saw. Phosphorus is another important impurity for silicon. It has an extra electron as well, 3s2, 3p3, one more than silicon, so it can give one to the lattice, as we will see. Okay, and then there's everything else. Less important. Germanium, we'll come to that. And gallium arsenide, we'll see it later on. Okay. Okay, so you see as we increase the electrons and as also the protons, the different elements are formed. But the electrons get added in a very specific manner, determined by these 4 quantum numbers. That's what I want you to keep in mind. Okay, so coming back to the electronic levels of silicon, we can look at the electronic levels also as shown here. Instead of just writing the quantum numbers, we can look at them. Okay, so this is the nucleus of silicon. Can you see it back there? Is it too small? Yeah. You can? Okay. So you see the 2s2 orbital is there, the innermost electrons. Okay. Then you have 3s2, which is shown there. Then you have 3p6, which is shown there. 2s2 and 2p6, they're very close together in energy. That's why they're shown close together in orbit. They're both quantum number 2, principal quantum number 2. And then you have 3. The 3, principal quantum number 3 represents the outer shells. Okay, so you have 3s2, those 2 electrons, and 3p2, which is an incompletely filled p subshell. Okay, remember P can have 8, right? It only has 2 here. Okay, and then you have other states as well, which are the so-called excited states. Of the silicon gets energy, it can excite into the outside states and relax and leave, release energy and so on. And we'll talk about that later on. But keep this picture in mind. Yes.
Why are the third level shells not as close together in the second level?
Yes, that's a good point, because of something called shielding of charge. We'll come back to that later on. So further away, the energy separation increases because you have lesser influence from the nucleus. Okay? And the inner electrons tend to protect the nucleus, so it prevents the electrostatic field from coming out so much. But we'll come back to that. Okay? Don't worry so much about it right now. We can, of course, also draw this in this format. In fact, I prefer, and we will come back, we'll probably draw it in this format mostly when we talk about crystals and so on, because this is the potential well. Okay, remember we drew the infinite potential problem last class. You can draw the potential well of the nucleus as a simple parabolic potential like that. Okay, it's approximate. And then the different energy levels are represented by these lines. So increasing energy up in the vertical axis. Okay, so you have n equals 1, n equals 2, okay, n equals 3, there's 3s, 3p. So you can see as the energy levels go higher and higher up, they get further and further from the nucleus and easier to be removed from the nucleus. So these outer electrons are what contribute to conduction, forming bonds, and so on and so forth. The inner electrons really don't do much, okay, because they're very tightly bound to the nucleus. Keep that in mind as well. Okay, so the orbitals as we drew here were just simple circles, okay? But if you actually solve Schrodinger's equations, the wave function has some shape. Remember in the potential wheel, well, we had the sinusoid, we had the cosine, and so on and so forth. We have different shapes. In this hydrogen atom, and also for silicon, the exact same thing happens. Different orbitals are not just little spheres. They have different shapes, okay? And we won't go through the details of what they are, but we'll just say what they are, okay? The S shell is basically spherical. This is a spherically symmetric shape. Okay, this is where m is 0. And remember, when m is 0, there is no phi dependence. Remember, m is the phi quantum number. If there's no phi dependence, that means it's spherically symmetric. If you think about the wave function. In any case, okay, that's S. The p orbitals are dumbbell shaped like this, and they can be oriented in Y, so you can have py, px, and pz. So 3 different options, and each of them can have 2 electrons because of the 2 spins. So you have 6 states. Okay, p has 6 states. It turns out, in a silicon lattice, when the atoms are very close together, the S, remember the last orbitals of silicon are 3s and 3p. There's 3s2 and 3p2. The s and the p orbitals actually interact because they're very close together. Okay? And they form what are called mixed orbital states. These are also called hybrid states. They're referred to as sp3 states. So you have 1s and 3p possible states mixed together. And they form a state which kind of looks like that. Okay? And you will see why this is in a second also. You will see there's a higher probability of finding. So remember, these represent probabilities of finding electrons, right? Remember, this is the wave function. So S means that the probability of finding the electron is symmetric. Anyway, equidistant from the nucleus. This means, the P means that there is 0 probability the electron is right at the nucleus. There's high probabilities here and here. Okay? In the mixed states, you can see there's a very high probability that the electron is here compared to here. So you see an asymmetry. And you will see that is the covalent bond. There is another silicon atom not shown on this side which has an equivalent orbital. And they overlap and they get held together. Okay? We'll see this in a few minutes. Okay. Oops. I guess that's what I said here. I don't know if you can read it. And many atoms are close together. The orbitals overlap and form mixed or hybrid orbitals. Okay, that's whatever I just said. Okay, now we kind of know how electrons are distributed in atoms. The question is, what happens when you bring the atoms together? Okay, we'll look at this qualitatively first to get a sense of what it is, and then we'll look at it a bit more quantitatively, okay, to understand energy bands. So first of all, we need to understand why atoms come together, because they have bonding forces, the forces which bring them together. It's a lower energetic state for atoms to be together than by themselves. So for instance, if you think about hydrogen, hydrogen rarely exists as a single atom. Usually exists as 2 atoms together, a hydrogen molecule. Right? Hydrogen molecule. This is because it forms a bond. 2 hydrogen atoms form a bond, covalent bond. They have an extra electron. Each of them have 1 electron. They share. to form what's called a mixed orbital, essentially. Okay? And there are three different kinds of bonding forces in solids, which we'll look at a bit more carefully. The first is what's called ionic bonding. This is what exists in sodium chloride and any kind of ionic materials. Could be potassium, some kinds of metals, and so on. In any case, sodium chloride is a very specific example. It has a face-centered cubic lattice, fairly simple. Okay, you have sodium, you have chlorine. Sodium has an extra electron in the outer shell, which it can donate, which loses its electron, and chlorine has an extra energy level, which can gain that electron. Okay? So what happens, essentially, is that sodium loses an electron, becomes a sodium ion, and this is a stable state because all the shells are filled. And chlorine gains this extra electron and becomes another ion, also filled shape. All the shells are filled. Very stable state. Of course, they're oppositely charged, so they have electrostatic attraction. They come together. They're very strong forces, hold them together. That's how you get salt, sodium chloride. Okay, forms a face-centered cubic crystal. And a stable equilibrium is reached when all the forces balance each other. Attraction, repulsion. Because you have a whole bunch of ions, right? It's not just two. So you have some sodium ions also nearby which will repel them. And you have chlorine ions also repelling, but these attract. So you have some equilibrium that forms. Okay? So the outer orbits of sodium and chlorine of these ions are fully occupied. This means that all electrons are tightly bound. They cannot escape. There are no free electrons. Okay? No free electrons that are able to move freely throughout the crystal, which means it's a poor conductor. Okay? So in ionic bonded solids are poor conductors in general. No electrons. So salt is a poor conductor, electricity and heat. Okay? Another form of bonding is the metallic bonding. This is fairly straightforward to understand. Metals typically have 1, 2, or 3 electrons in the outer shell. Okay, they're very weakly bound. They're far away from the nucleus typically, so they are easy to be lost. Okay, and they're very easily given away into the crystal lattice. Okay, and the outer shell is only partially occupied, which means there's lots of energy levels so that the electron can hop into from one atom to another. Okay, it's easily seen if you look at aluminum, which is in a metal. So you can see the 3 valence electrons are shown here, and they're weakly bound to the nucleus. So if you bring the atoms together to form a crystal, these electrons will spread out. They can go from one atom to another very easily. Okay, and the picture is as follows. In the crystal form, these electrons are readily given up by the nucleus to form a common cloud of electrons. So as opposed to sodium chloride, where one electron was given up and that electron was taken away from the crystal, sodium gave away an electron, chlorine took that electron, so there are no more electrons available for the crystal. In a metal, the electrons are given up. It's like a cloud. The electrons are just shared between all the ions. So if you look here, so you see the nuclei have positive charges, and you have a cloud of electrons represented by this V. Okay, just delocalized across the entire crystal. They're shared by all the ions. So this electron cloud, of course, has a negative charge. Ions have a positive charge. It's electrostatic attraction. Forms a crystal again. In the case of aluminum, it's again a face-centered cubic crystal. But now, the point is that there's a cloud of electrons which are very mobile. They can move very easily. So if you apply an electric field, electrons will move and form current. So metals are good conductors of electricity and also heat. Heat's also conducted by electrons, same way. Okay? We won't deal too much with heat. We'll deal with electricity. So. Okay. Aluminum forms an FCC crystal lattice, and again they're held together by electrostatic forces. So you have an attractive electrostatic force between the ions and the electron cloud, and of course you have repulsive electrostatic forces between the ions themselves because they're all positive, or the electron clouds themselves. So again, it reaches an equilibrium to form a crystal lattice, which determines the spacing between the ions and so on and so forth. Okay? The last bonding is the covalent bonding. Okay, this is important form of bonding because this is what most semiconductors are that we're interested in. Silicon, gallium arsenide, germanium, so on and so forth. Okay, all the diamond lattice semiconductors. We remember diamond lattice we saw before, where it was two FCC lattices which are displaced from each other. Okay, they have 4 electrons in the outer shell, carbon in the form of diamond, silicon, germanium, etc. Each electron of an atom is shared with 4 of the nearest neighbors in the diamond lattice. Remember the three-dimensional picture we saw before? The 2 shared electrons form a covalent bond. So each silicon atom has 4 electrons in the outer shell, and it has 4 neighbors. So there's 1 electron is shared with that one electron is shared with that, 1 electron is shared with that, 1 electron is shared with that. And each shared electron is a covalent bond. Okay? And we'll come back to that again. If you recall, each of these shared bonds is that sp3 hybrid orbital, where the fat portion of the sp3 orbital is actually between the atoms. Okay? That represents where the higher probability of finding the electrons is at the covalent bond. Okay? Other examples are hydrogen molecule, as we talked about, and so on and so forth, and germanium and all that. Okay? Now, if you think about it, there are no free electrons available here as well. Right? They're all they're bound by the covalent bond. They're bound to the nucleus. So these are co-conductors as well. Okay? But the key point for semiconductors, again, to reiterate, is that their conductivity can be changed. You can introduce impurities, or you can introduce energy, optical energy, thermal energy, as we will see on Thursday. Okay? You kick the electron out of the bond, and then you have free electrons. Okay? So if you kick the electron out of this bond, those electrons can float around and then conduct electricity. That's basically what happens in a semiconductor. Okay? We'll see that in a bit more detail on Thursday. Okay. You can also have something called a mixed bonding, which is essentially a combination of both covalent bonding and ionic bonding. So it exists in things like gallium arsenide. It's less important, but in terms of in gallium arsenide, you have 2 different nuclei, gallium and arsenic, and there are different charges. So you can imagine, because of the different charges, you can have different electrostatic forces in addition to the covalent bonding. So you have this covalent bonding effect of these overlapping orbitals, but also electrostatic forces which hold them together. Okay? And you can have varying effects of each, depending on alloys or compound semiconductors. Less important for our discussion right now. But just be aware of it. Okay, the last topic for this week I want you to think about is energy bands, and we need to cover this to really be on track for Thursday. Okay? Now, so far, what we have thought about have been single atoms in terms of energy levels. They form discrete energy levels. It turns out when you bring multiple atoms close together, these energy levels start behaving strangely. They form bands. Instead of being discrete, they start to become continuous. Let's try to understand why that is the case. Okay? So as individual atoms are brought closer together to form a crystal, an equilibrium between attractive and repulsive forces is reached. Very similar to what we talked about in the crystal. Remember, the nuclei try to repel each other because they're both positive if you bring 2 nuclei together. And the electron clouds and the other nuclei attract each other because one is positive, one is negative. Okay? As the electrons see the effect of neighboring nuclei, the discrete energy levels spread into energy bands. Okay, so how does this work? Let's look at the simplest possible problem, which is the 2 atom. Okay, let's just take 2 atoms which are far apart and bring them closer together. Let's think about what will happen to their energy levels of the electrons of each of these atoms. Okay. So first of all, let's start with the potential of the individual atom. So it looks like that. Okay, very similar to what we just saw. But these dashed lines represent the like potential wells from the nuclei when they're far apart. Okay, no distortion. They don't see each other. The two atoms don't see each other. Okay, so the Coulombic potential well of a single atom. Now, as you bring them closer together, so of course, for each of these atoms, we have one wave function. Okay, kind of looks like that, let's say. Remember, we have the bonding and the anti-bonding. Oh, no, we haven't seen that yet. We'll see that in a second. But we have the wave function, which looks like that. Okay, remember, this is, let's say, the 1s orbital. Okay, and there are two of them for each of the atoms. Okay, they're far apart. Nothing has happened yet. Now, as we bring them closer together, they start seeing each other. So the potential starts changing. In particular, the potential in between starts decreasing when the atoms are close. This is because if an electron is there, it is attracted by both the nuclei. So remember, our Coulombic potential was proportional to Q squared, charge squared. So if you have two nuclei, you're double the charge. You squared, you're 4 times as much potential. And it's negative, remember. So it goes down. Okay? It's not, that's approximate because they have to interact, but approximately, they go down. So you can see the actual potential well actually goes down in between, forming a shape like that. And the atoms are close together. Now, of course, that also means that the electronic wave functions have to change as well, right? Because the potential shape has changed, and the potential shape in the Schrodinger's equation determines the wave function of the electrons. Okay? So those are the individual electronic wave functions, psi1 and psi2, when they're far apart. But when they get closer together, they actually start interacting. Okay? And they form, and you solve the Schrodinger's equation for a coupled potential wave function, potential function like that, you get what's called a composite 2-electron wave function. Now the electrons are no longer separate. They see each other, and you have a 2-electron wave function. Okay? Which means you have one wave function which describes both electrons. It's a little bit abstract. Okay? Because it turns out the solution for this sort of Schrodinger's equation with this sort of potential gives rise to two different wave functions. Okay? One is what's called an anti-bonding orbital, and one is called a bonding orbital. And you can see the clear difference between them. In the anti-bonding orbital, there is zero probability that either electron will be right in the center. Whereas for the bonding orbital, pretty high probability that the electron will be in the center. They're very different. They're very different shapes. Okay? And they're also even and odd. Okay? One is an odd function and one is an even function. Okay. These can also be thought of as a linear combination of the individual atomic orbitals. So it can be thought of as psi1 plus psi2, or just psi1 plus e raised to with the phase shift psi2. Okay, so these can be also solved as linear combinations of orbitals. And this is, in general, what happens when you have complicated arrangements of atoms. Your electronic states from individual atoms start forming linear combinations of solutions. Okay? And you can kind of see why this happens because you can think of, to a zero-order approximation, the potential is a linear combination of two potentials. Okay? And Schrodinger's equation is a linear. Okay? So you can actually solve this as two different Schrodinger's equations. You get two different solutions and add them together to form the final wave function. Okay? In any case, you can keep that in mind, less important. So in any case, what happens essentially is that, so it's an odd functioning, is that for the bonding orbital, you see a higher probability of finding the electron in between the two nuclei when R is 0. And now if you look here at the potential, that's where there is a lower potential. So potential energy is lower, which means now we know that this function, this wave function, should have a lower energy level compared to that function. Right? Just intuitively. without even solving for the equation. Because we know that the electron spends a lot of time here as opposed to here. There's nothing here. So for this wave function, the electron sees more of this potential, which has a lower value compared to the electron here. So we can say intuitively that the wave function here has to have a lower energy value than that. And of course, that wave function is what forms the covalent bond. So it's called the bonding orbital. Okay, this is the so-called sp3 that we saw before in silicon, the equivalent one for silicon. Okay, so this region has lower potential energy, so the bonding orbital has a lower total energy than the anti-bonding orbital, which means that this single energy level for the individual atom now has split into two, a lower energy and a higher energy. Okay, so just by bringing two atoms together, one energy level became two. Okay, and this is essentially what happens as you bring many atoms together. Without going into the math, we can make the conjecture that if I bring 3 atoms together, one energy level of each of the atoms splits into 3. If I bring 4, they split into 4. If I bring a million, they split into a million. And they're all close together, so it basically forms a distributed set of energy levels, which is basically a band, a continuous distribution of energies, no more discreteness. Okay? So basically, that's a qualitative way of understanding formation of energy bands, which is a very important concept in semiconductors. Okay? So you can look at it in a slightly different manner using the Pauli's exclusion principle. Okay? When the atoms are, of course, far apart, let's say you have two silicon atoms which are very far apart, they don't see each other, the outer electrons can have the same quantum numbers. The exclusion principle doesn't disallow that. So you can have, the 4 outer electrons have the same quantum. You can have an electron here with same set of quantum numbers as the electron there, let's say. But as you start bringing them closer together, they become they share wave functions. Then the Pauli's exclusion principle kicks in, and you cannot have that anymore. Those two electrons now have to occupy 2 different sets of quantum numbers. So you can see, let's say this electron and this electron occupy the same energy level when they're far apart. When they get close together, they cannot occupy the same energy level. That's what exclusion principle says. They have to split into 2, at least. Okay? When they're close together, exclusion principle forces 2 electrons to have 2 different sets of quantum numbers and hence energy levels. So that's another way to look at the splitting phenomenon. When you have many atoms close together, this leads to energy bands, so continuous distribution of energy levels. Okay? Okay, so let's see how that works, because that's also a bit complicated, and what for the purposes of this class, we need to understand this qualitatively, okay, conceptually. So the picture is shown as follows. The horizontal axis here represents distance between the silicon atoms. Okay? The vertical axis is essentially the relative energy of the electrons in each of these atoms. Okay? And when they're out here, the atoms are infinitely far apart. They're individual states, just like we saw before. The isolated atoms, and they have these energy levels. Okay? 2s2, 3s2, 1s2, 2s2, 2p6, and 3s2, 3p2, right, over here. You have 4, so the outer shell has 4. There should be 3 and 1, yeah. Right? Okay, this is just individual atoms we saw before. As you start bringing them closer together, you see these discrete states now spread out into bands. Okay, so the outer shell has 2 3s and 2 3p electrons. When they get closer and closer together, they merge into a single band, as shown here. Okay, so what's happening here is that each of these electron states will split into 2, then more into 2, and so on and so forth, into very many. Okay, And you can see there are 6 ends, 8 end states here. If you bring 8 end electrons together, n atoms closer together, you have 8 end states, which is obvious. In the outer so you have 6 end states here, 2 n electrons here, whereas you have 2 n states here, 2 n electrons here. Okay, available states and electrons to fill those states. Then, at the equilibrium location, which is the distance of the crystal lattice, you form an energy band. Okay, these bands now split into 2, where you have a bottom band where all the states, there are 4 n states, there are n atoms, are all filled with 4 n electrons. There are no free states here. Okay, and then there's an energy band gap. And then you have 4 n states also in the top band, but there are 0 electrons there. They're totally empty. Of course, that's the semiconductor. Completely filled valence band, completely empty conduction band. Okay. Then we also see that there's a band gap, that there are no allowed energy states. So no electrons can actually occupy those states. Okay. These are very important properties of the semiconductor. Okay, 4 n states there. So the valence band is completely full, the conduction band is completely empty, and that determines a semiconductor. Okay. Now we can look at this we can look at this same principle of what happens to the energy levels to form bands for different kinds of materials. What I showed you was for silicon, because it's a semiconductor. For metals and insulators, they're slightly different. Okay? So, and the reason to understand this, because if you come back here, because there are no free states here, they're totally full, and there are no free electrons here, they're totally empty. This is an insulator. There are no free electrons, and there are no free states. You need electrons to be able to move. Okay, that doesn't exist yet. There's another way to look at what I said before in terms of the covalent bonding holding the electrons tightly together so they're not available to move around. So silicon is an insulator. Okay? So for electric conduction, there must be free electrons and unoccupied energy levels for these electrons to move into. So you have to have 2 things. You need to have electrons which are free to move around. You need to have energy levels those electrons can move into. Okay? One of those don't exist. It's a poor conductor. Okay. So this is a way to look at it pictorially. So you have a valence band which is completely full, no free energy levels. So even if an electron wants to move here, it cannot, because it doesn't have an energy state to move into. Okay? This is energy gap, and then you have a conduction band. There are no free electrons. There's plenty of energy states, but there are no free electrons to move. So it's an insulator. Okay? On the other hand, if you look at metals, so let's look over here. If you look at a metal, the energy band of a metal looks as follows. You have a filled band, you have a partially filled band. So you do have some electrons here, and you have lots of states here. So the electrons can move very easily. Or you can have an overlapping bands. Okay? So there's plenty of free electrons, plenty of free states. So the electrons can move very easily. This is another way of saying what we saw before, that there was an electron cloud associated with the crystal lattice of the metal. This cloud is able to move freely. Okay? In the case of a semiconductor, is what we just saw, just that. In the case of an insulator, it's exactly the same as a semiconductor, except that the band gap is much larger. Okay? So it's only a quantitative difference. Yes?
So if you were to use an insulator the same way as a semiconductor with higher energies, then it would totally be the same. You could still do transistors and all that.
Yes.
But it would take a lot more energy.
Yes, but there are other problems which come into play. When you say more energy, you can cause other damage and so on to the crystal.
Right.
So from a practical perspective, that's, I would say it's, most insulators cannot be used as semiconductors. Okay? But it's a quantitative difference. Qualitatively, they are the same. Okay. So, by the way, you notice I said this is the energy bands at 0 Kelvin. It's at no thermal energy. As you will see later on, at room temperature, at higher energy levels, these electrons here can get thermal energy and get excited into the empty states. And then it becomes a conductor. Okay? We'll see that actually as shown here. So you can have thermal or optical energy which can excite an electron here. Then the semiconductor can become a good conductor. Okay? The same thing can also happen with dopants. We'll talk about that also. Okay? Okay, I think we'll stop here because I covered a lot. So we'll cover this on Thursday. So remember, for those of you who came in late, the homework is already posted online, and the homework's due on January 28th. You can either email in your solutions, or you can print them out or write them out and submit it to the department. I'll make sure there's a box, and I'll let you know on Thursday. And we will have a review session on Friday. Okay, last Friday was canceled because of the snow. Just 1 second.